The following list are the parent functions. Most of the functions that we see in this class are going to be based on these things. So understanding their very basic behavior and understanding what they look like is going to help knowing what to expect when using them. The first one we've already seen, and that is a linear function. And this, of course, is just f of x equal to mx plus b. Of course, this actual parent function, I should just say, is just x. So the slope of 1 and then a y-intercept of 0, that gives you this parent function, just a solid line there. You'll also see this line labeled as y equals x. That's the very basic line there. It's called the identity function because the input is the same as the output. The domain for these linear functions is everything. And the range is also everything. You can see it goes left and right. It continues leftward. It continues rightward. It continues upward. And it continues downward. So the in behavior, you can see, of course, that it goes up to the right and down to the left. So we can write the in behavior as x goes to positive infinity, f of x goes to positive infinity, x goes to negative infinity, f of x goes to negative infinity. Okay, the next parent function, this is the absolute value. This thing looks like f of x equal to the square root of x. That's this graph here. The domain, of course, is everything. It goes left and right continuously. And the range, you can see the lowest point is right here at the origin. It does hit that point, so 0 up to positive infinity, because it doesn't, it goes upward both to the left and to the right. So the in behavior, of course, is positive infinity this way, positive infinity that way. So x goes to positive infinity. F of x goes to positive infinity for both. Okay. This is the quadratic function. We're going to be looking at these a little bit more in depth here soon. This is going to be f of x equal to x squared. That's the parent function with nothing else in it. And you can see the domain. This is very similar to the absolute value, which it may not go, the absolute value was like this. It may not go left and right as fast, but it does go up faster, but it does go left and right continuously. You just have to zoom out far enough and it'll meet all of this stuff. So the domain is negative infinity to infinity. The range is once again 0 up to positive infinity. And you can see it goes up and up, the left and right. It always goes to positive infinity, no matter which direction you're going. This is what's called the inverse function. It's not quite the inverse of this, but we're going to be looking at these a little bit more later on. This is the square root. If you square something, the thing to get rid of that square is the square root. And the parent function is the square root of x. It just starts here and then goes up like this. It does, in fact, go upwards continuously. It just gets, it just very slowly goes upward. So the domain, you can see it does not go to the negative because you cannot have negatives underneath of it. So the domain is 0 to infinity. The square root of 0 is 0, so there's no issue there. The range is also 0 to infinity. It goes up very slowly, but it does go up. All of these values up here are reached at some point down in the domain. So, and you can see there's really only one in behavior, and that's to the right. We have x to infinity, f of x goes to infinity. And that's all there is to it for the end behavior. It doesn't go left at all. Okay, the next parent function, this is the cubic function. This is just f of x equal to x cubed. And there's no issues with cubing any number, so every number can be cubed. That means the domain is everything. And you can see it goes down indefinitely, it goes up indefinitely, so the range is also everything. The end behavior, of course, it goes up to the right and down to the left. So as x goes to negative infinity, f of x goes to negative infinity, x goes to positive infinity, f of x goes to positive infinity. Okay, how do you get rid of a cube? Take a cube root. So this is a cube root. That's going to be the cube root of x is the parent function. And this clearly it has the domain of everything. There's no issues. The range, it does go up and down very slowly, but it does go there. So everything is in the range. And the end behavior, of course, it goes up and down, just like the cubic function does. It's just very slow to do that. So it's the same thing as this, really. Okay. This is the exponential function. And this has different choices of bases. This one looks to be, I'm not sure. I'm going to say that's probably E, but it's just B to some power X. B is some real number, not zero, or it can't be negative, I should say. B is greater than 0, not equal to 0. And B is, well, specifically this one looks like B greater than 1. There are plenty of transformations on this. If B were equal to 1, 1 to any power is just 1, so you actually get a flat line, and that's not what this function is. Now, this is B greater than 1. All functions with B greater than 1 look like this parent function. That's the reason why this is the, we're just using a generic graph for it. This graph is a specific B, of course, but it doesn't really matter because they all look similar to this. The domain is everything. You can take any power on B, like you can take 1, 2, 1.5, 86.37, all those things. You can take a single number like 2, for instance, 2 to some power like that, and you can find it. So there's no issues with the domain. And the range, you can see, well, if you get a very, very small negative number, for instance, if we had 2, and we put some very small negative number like 2 to negative 100, this is the same thing as 1 over 2 to the 100. This is a very, very small number. And the bigger this number gets, the bigger the denominator gets, therefore it gets even smaller. And in fact, it gets so small that it never gets to 0, no matter how large of a negative number you choose. It never gets to 0, but it gets as close as you want. So we're going to say 0 to infinity. It never equals 0, so you don't use a square bracket, but it does get all the way to 0. And the end behavior, of course, this is just flatlining to 0. So as x goes to negative infinity, f of x goes to 0. On this side, it goes up to positive infinity. Okay, the next one here, this is the logarithm to get rid of a exponent. Not an exponential like number. That would be a root that you take, a radical. In this case, the exponent has the variable, and to get rid of a number in the base, you have to take a logarithm to get rid of it. So this basic one is log base b. Again, you have to use some kind of base, and b is going to be greater than or equal to 1, or sorry, greater than 1 for this case. And all of them look very similar, just like the exponential have very similar graphs for any number b it's greater than 1. This one also looks very similar. The domain, you can see it stops. It actually shoots downwards towards negative infinity here. and it never crosses this y-axis. It never touches it. So the domain is actually 0 to infinity. And the range is, well, it goes all the way downward. And this is actually one of the, if not the slowest function to increase. It does go up to positive infinity. It just takes an incredibly long time to do so. So the range is actually negative infinity to infinity. Okay, the end behavior. There is no end on this side. X just stops there. So all we really can say is as x goes to positive infinity, f of x goes to positive infinity. It doesn't at all go down towards negative infinity. So it's really only this one in behavior. It just takes a long time to do that. So those are the basic parent functions. The next set I'm looking at here are what are called trigonometric functions. These are going to be, we're going to look at these more in depth. But for now, we're working with the regular ones. But I just wanted to show these because this is all the parent functions. This first one is the sine function. It looks like this. Sine of x. And this is all it does. It just kind of waves up and down. You can see that the domain is different here. It's in terms of pi, and you'll see why that it's that way. So the domain, it does go left and right indefinitely, so the domain's everything. The range, however, I haven't shown this here, but the range, this is actually -1, and this is +1. And it does not go below or above that mark. So the range is -1 to 1, including both. Now, I don't have end behavior down here, and that's because these functions don't really have end behavior. They keep doing this pattern where they go up and down, up and down, up and down. Therefore, there is no end behavior for these. It's always this changing quantity. Now, as I've been showing before, the inverse of, how to undo the square, you take a square root, cube root, exponent, the logarithm. The way you get rid of the sign is you take what's called the arc sign. And that looks like this. You can write it as arc sign, or you can write it as sine inverse of x. We'll talk about what are inverses a little bit later on too. And this is really just a small portion of the sine wave. Again, we'll show that. But this is what it looks like here. That's the typical representation. You can actually have different ones depending on where you're looking at. But this one's the typical. You can see the domain goes from -1 to 1. And the range goes from -π/2 to +π/2. Again, there's no end behavior. It doesn't go indefinitely left and right. So that's all there is to it. Okay, the next function is the cosine, written as cosine of x. Once again, the domain is everything, and the range is this bounded between -1 and 1. The lowest point it goes, the highest is at +1. So that's the range. The arc cosine, or the inverse cosine, or you can write it as cosine inverse of x. This has a domain from -1 to 1, and a range, in this case, from 0 to pi. All right, the next one here, this one's going to be a little bit weird, but this is just tangent. So this is going to be f of x equal to tangent of x. The domain here is a little bit strange. There are actually these sharp peaks where it goes all the way upward. and it doesn't actually cross this value here. This is what's called an asymptote. It gets infinitely close to this point, but it never crosses it. And then it jumps down to be down here, and it continues this pattern. Then it jumps down, continues the pattern, jumps down. So this is located at, let's see, if this is 2 pi, that's going to be pi over 2, pi, 3 pi over 2, 2 pi. So it's going to be pi over 2, 3 pi over 2, and every multiple of that. So the domain, I can write it like this. Let's see. Write it like x cannot equal pi k plus pi over 2, where k equals 0 plus or minus 1 plus or minus 2, and so on. So what this is saying is that x, so we're including x being a real number, all real numbers, except, or I can say like this, x element of the reals, except x does not equal pi over 2 is this spot right here. That's this one right here. If k were 0. If k is 0, you get 0 times pi is 0 plus pi over 2. That's just pi over 2. Now if k is 1, you get pi here. Pi plus pi over 2, that's 3 pi over 2. That's this line here. The next one is when k is 2, 2 pi plus pi over 2, that's this point right here. And then continues every two jumps, you have another asymptote where it cannot equal that. And then you can also go in the negative direction. Negative 1 times pi is negative pi plus pi over 2. That's this spot right here. Negative 2 pi plus pi over 2 is this one here. Negative 3 pi plus pi over 2, this one here, and so on and so forth. Of course, the range is everything. It goes all the way down and all the way up. So that one's pretty easy to do. Now, the inverse of this, the arctangent or inverse tangent, this one has a domain of everything. You can see it goes left and right completely. And it goes up, but it actually gets infinitely close to pi over 2, but never quite touches it. The same thing is true for negative pi over 2. It gets very, very close to it, but never crosses that. So we're going to write it like this. That's the domain of this function. It never crosses this horizontal line. Okay, that's that parent function. Once again, these are probably confusing, but we will be looking at these later on. Okay, the next function I have here, I believe, is secant, or probably cosecant actually. Yep, cosecant. This is going to be f of x equals CSC of x. That stands for cosecant. The domain for this one, again, has a very similar thing to the domain of tangent. We have an asymptote here at 0, one here at pi, one here at 2 pi, same thing at negative pi, negative 2 pi. So x is an element of the real numbers. That's the domain, but x cannot equal pi k, where k equals 0 plus or minus 1 plus or minus 2, because 0 would be here, right? K times 0 times pi is 0. X cannot equal this one. This is at plus 1 k. Plus 1 times pi is just pi, and that's where that one is at. Then 2 pi, negative 2 pi, and so on. The range that actually bottoms out here, this is at 1. And this point here is at negative 1. So the range is everything from negative infinity up to negative 1, including it, union with 1 to infinity. It never goes between the -1 and 1 portion. Okay, this is arc cosecant or inverse cosecant. So f of x equals, or cosecant inverse. The domain here is everything from -infinity to -1. I believe it can be equal to -1. Unioned it with 1 to infinity. Okay, and you can see there's that gap there between -1 and 1. That's why we have an opening there. And then the range, well, the lowest value it hits is -pi/2. And you can see it goes upward and upward and upward, and it gets all the way close to 0, but it never hits it because it actually jumps to this side, and then it goes all the way up to pi/2. So it actually goes to 0, but never touches 0. So I have to remove 0 from that interval. But it goes from -pi/2 to pi/2. This next one is secant, written as f of x equals secant of x. This one has a, you can see that there's another this portion here between -1 and 1, just like cosecant. That portion is not involved in the range, and the domain has these asymptotes again at every one of these markers. So that's going to be, this one's pi/2, so it's going to be pi/2. X cannot equal, so of course x is an element of the real numbers. It's all real numbers except for pi/2 plus pi k, when k equals 0, plus or minus 1, plus or minus 2, and so on. And when k is 0, right, that's going to be pi/2. That's going to be this one right here. When k is plus 1, it's going to be pi/2 plus pi. That's going to be this one here. Then k equals 2, k equals -1, k equals -2, k equals -3, and so on. The range, like I said, is from -infinity to -1. Union with I can equal 1 and -1. 1 to infinity, just like it was for cosecant. And the inverse function, the inverse portion of this, is going to be arcsecant. So f of x equals arcsecant, or secant inverse of x. And that has a domain, everything up to -1, including it, union with 1 to infinity, off to the left and off to the right. And the range, of course, you can see, well, it goes from 0 up, and it gets close, infinitely close to pi/2, but never crosses it. And it jumps over here and goes up to pi. So pi/2 is not in the range, but everything up to pi is. This one here is the cotangent function. It's our last parent function for the trigs. Cotangent of x. Domain is, you can see that it's every pi that's been removed here. So we're going to say x element of r. X cannot equal pi k, where k equals 0, plus or minus 1, plus or minus 2. And the range is everything. It goes down and up infinitely. Of course, we have the arc cotangent, or f of x equals also cotangent inverse of x. This has a domain of everything. It goes left and right infinitely. And it has a range of, gets close to 0. It never crosses that line, and it gets close to pi, but never touches it. So from 0 to pi. Now I should say that arc cotangent, and I believe it was arc tangent, as well as arc cosecant and all those do have end behaviors, right? This one goes infinitely. As you go to the left, it goes to pi over 2. As you go to the right, it goes to negative pi over 2. Our cotangent goes to pi as you go to the left, and it goes to 0 as you go to the right. And so that's kind of the end behavior of these special functions. But most trig functions don't have end behavior, like you can see here. For regular cotangent, it's just this constant, what's called a periodic behavior. So it does not have a end behavior, because it's the same thing continuously forever.